Welcome to this video on ordered choice. Ordered choice is a direct extension of binary choice to a setting with a linear index and more than two alternatives. What is important here is that these alternatives have a natural ordering. So that means that we have an ordering here that everybody can agree on. So examples are number of children, more is more, level of schooling. It's clear what means more schooling and what means less, and health. Let's describe the model that we'll look at here. So in the model, we have capital J alternatives, and these alternatives are indexed by little j. Little j runs thus from 1 up to capital J. Then in this model, there is a latent variable. Latent means unobserved, and this latent variable is going to be denoted by yi star. And yi star is xi beta plus epsilon. Moreover, we'll have unobserved thresholds, and these are going to be denoted by alpha 1, alpha 2, up to alpha capital J minus 1. Now, if these thresholds are actually observed, then we have what is called an interval regression model. To see this, let's look at the observation rule that we will always have in this model. The observation rule is that in my data, I'm going to observe a value for yi. So that runs from 1 up to capital J. And I have here the details that tell me how values of yi star are translated into values of y. So if yi star is less than or equal than alpha 1, then I'm going to observe a 1. If it is between alpha 1 and alpha 2, I'm going to observe a 2, and so on and so forth. And for the last outcome, if yi star is bigger than the last threshold, alpha capital J minus 1, then I'm going to observe a j. Now, if these thresholds are observed or known, then I said we have an interval regression model. So let's say income is recorded not in terms of euros, but in terms of intervals. Okay, so let's think of income per year. So income per year is coded as a 1 if income per year is less than 20,000 euros. Is coded as a 2 if it is between 20,000 euros and 24,999 euros. 24,999 euros. Okay, so in that case, you actually do know these alphas, but you do not observe the actual income, but you observe in which interval income is. This latent variable has two parts. There is an xi beta part, and in the end of the day, we're going to be interested in beta, the parameter on x that leads to higher or lower values of yi star. And epsilon I is going to be our econometric error term that captures unobserved differences across individuals. Now, you can already probably see some parallels to the binary choice model. These are not exactly the same in terms of the structure, but we can get out of this structure here, we can get a binary choice model when we set j is equal to 2 and alpha 1 is equal to 0. In that case, we get a model that can produce the exact same choice probabilities. And to see this, let me just write this out for you. So before, what we had was that yi is equal to 1 if xi beta is greater or equal than epsilon I. So what we got from that was that the probability that yi is equal to 1 given xi was the CDF of epsilon I evaluated at xi beta. That was our choice probability for the higher of the two outcomes, higher in terms of the coding, right? So yi is either 0 and 1 or 1, and here this is the probability to observe the higher of the two values. Now, for the order choice model, what I can do is to write this down for the special case in which j is equal to 2 and alpha 1 is equal to 0. So what I get then is that yi is going to be equal to 1 if yi star is less than or equal than alpha 1, and yi star is going to be, just going to write this down here, yi star was xi beta plus epsilon I. So I need here yi star is less than or equal than alpha 1, and alpha 1 is equal to 0. So 0, and I get yi is equal to 2 if yi star is greater than 0. Again, this is alpha 1. And yi star, of course, is this. So let's look at the probability for this outcome here. So the probability that yi is equal to 2 given xi is going to be equal to the probability that yi star is greater than 0. So yi star is this. So it will be xi beta plus epsilon I is greater than 0 given xi. And what I'm going to do here is actually later in the slides, I'm going to make the exact same assumption as before, namely that xi is independent of epsilon I. Okay, so if I do that, then I'm conditioning here on xi. So this xi is going to be this same xi here, and I can write this unconditionally because I'm basically putting the xi in here. Let me do that right away. So it's the probability xi beta plus epsilon I greater than 0. So this is the exogeneity of xi. Now this is the probability. Let me write this down in many steps. That that epsilon I is greater than minus xi beta. I'm just bringing this to the other side. Like this. And of course the probability, since I have only two outcomes, no, this has nothing to do with these two outcomes. The probability that epsilon is greater than minus xi beta is equal to 1 minus the probability that epsilon I is less than or equal than minus xi beta. Okay. Now let's think about whether we can rewrite this term here to arrive at something that looks like this. Up here that we have seen for the binary choice model, which was the CDF of epsilon I evaluated at xi beta. And the easiest way to see what we have to do is to actually draw a figure. So let me draw a figure like this. Let me just draw a CDF. Okay, and let's say this is the CDF of epsilon. And let me say, okay, let's think of xi beta as positive. The argument holds more generally, but it's easier to write it down like this. So minus xi beta will be here, and of course xi beta will be here. Now the CDF is point symmetric, so here I'm going to have 0, and this is going to be 0.5. And now what I'm looking at here is 1 minus the probability that epsilon is less than or equal than minus x beta. So what I'm looking at here, this quantity here, is actually this quantity here. So let me write that down. 1 minus the probability that epsilon I is less than or equal than minus xi beta. Now, because of point symmetry, this quantity here is equal to this quantity here. And we know what this quantity here is. This is the CDF evaluated at xi beta. The CDF of epsilon evaluated at xi beta. So let me just write that down here. Like this. So for that reason, this quantity here is going to be equal to the probability that epsilon I is less than or equal than xi beta. And by definition, this is the CDF of epsilon I evaluated at xi beta. So we arrive at this expression here, which is the exact same expression as we had for the binary choice model. What does that now mean? That means that both models that I've looked at here produce the exact same choice probabilities. And if they produce the exact same choice probabilities, you could say that the so-called empirical content of these models is the same. So they're slightly different in terms of the notation and the setup, but in the end of the day, what they generate in terms of tangible quantities, and I'm saying tangible because they correspond to what we observe in the data, these models are the same. Now, once I now go back to the general order choice model, what I can do is I can write down choice probabilities, and these are of course likelihood contributions. And you see them here on this slide here. So the probability that y is equal to 1 given xi is the probability for the lowest outcome, and that is the probability that epsilon I is less than alpha 1 minus x beta. You see here that what I've done is I've had actually x beta plus epsilon I on the left hand side of this inequality. On the right hand side we had alpha 1, so I'm bringing this to the other side, and therefore the probability for the first outcome is the CDF of epsilon evaluated at alpha 1 minus xi beta. For the second outcome, what I have is that the probability of, and now again what I've done is I've moved the xi beta part to the other side. Let's see. So it is the probability that alpha 1 is less than x beta plus epsilon is less than or equal than alpha 2. This follows directly from the model structure. So what I can also do is I can write this as the probability that alpha 1 minus x beta is less than epsilon is less than or equal than alpha 2 minus x beta, and that is again equal to the probability that epsilon I is less than or equal than alpha 2 minus x beta minus the probability that epsilon I is bigger than alpha 1 minus xi beta. I'm sorry, that's actually wrong. Let me write this down for you so that we can see this directly. Good. So I'm after the probability that alpha 1 is less than xi beta plus epsilon I is less than or equal than alpha 2. Okay, so that this is the probability that the latent index falls in between alpha 1 and alpha 2. Okay, so first of all, what I can do is I can rewrite this as the probability that alpha 1 minus xi beta is less than epsilon I is less than or equal than alpha 2 minus xi beta. So now I'm getting a probability that epsilon I, my econometric error term, falls in between these two quantities here. Okay, and now I can write this probability here as the difference between two probabilities. So this is the probability that epsilon I is less than or equal than alpha 2 minus xi beta minus the probability that epsilon I is less than alpha 1 minus xi beta. Okay, so this is very easy to see. So let's say here's my density for epsilon I. Here I have alpha 2 minus xi beta. Here I have alpha 1 minus xi beta. So what I want to have is this area here, namely the probability that epsilon is in between these two thresholds. So what I can do is I can say, okay, this is the probability that epsilon is less than this higher threshold. So this is this whole area here, minus the probability that epsilon is less than this lower threshold. And there's one last thing we have to do so that we can write this in terms of the difference between two CDFs, and that is to notice that the equality here happens with probability 0 if epsilon is continuously distributed. And this is what we're going to assume here in this model. And then what we can do is we can write this as the difference between the CDF of epsilon I evaluated at alpha 2 minus xi beta and the CDF of epsilon I evaluated at alpha 1 minus xi beta. And this is what you see here on this slide. Okay. What we're going to do, and this is again a big parallel to binary choice, we're going to make assumptions on a distribution of epsilon, and the two popular assumptions. One is normal distribution that gives us the ordered probit model, and to be specific, one assumes that epsilon I is usually standard normal. Sometimes one imposes the scale normalization in a different way, but the easiest way to go is to assume that epsilon I is a standard normal or logistic, and that gives the ordered logit model. And we're going to look at that actually in the next slide. So here you see again a plot with a density of epsilon. Again, this is for the ordered logit model. So this is the logistic distribution underlying this plot here. And I have now three thresholds here. You see here alpha 1 minus xi beta, alpha 2 minus xi beta, alpha 3 minus xi beta. So what you see in this figure here is you see basically three areas, right? And these are the three probabilities that we get out of this model. This is the probability that the outcome is the lowest one, y is equal to 1. Then the second area here is the probability that y is equal to 2. The third one is the probability that y is equal to 3. and here we have the probability that y is equal to 4 in our data. Now let's think a little bit about normalizations. You might have noticed already that we didn't have these alphas floating around when we looked at the binary choice model, and also here we have actually in this one example set alpha 1 equal to 0. But then in the more general case we need these alphas, but that begs the question, does xi beta have a constant term in it? So usually what's done is that xi is assumed to not include a 1 as the first element, so the xi beta doesn't have a constant term in it. What we have done instead in the binary choice model is we have assumed that alpha 1 is equal to 0. Now, these two things are doing more or less the same thing, or they are doing the same thing. You can go back and forth between them. But for different models, we have different ways of usually approaching this. And this is just important for you to keep in mind once you're wondering about normalizations. So this is the location normalization. And then on top of that, there's a scale normalization, as in the binary choice model. And the scale normalization works in exactly the same way. So one would fix the variance of epsilon I, usually at a particular value. And this is done by making a distributional assumption. So in the ordered probit model, that variance would be set to 1. Reporting of results. This again is a parallel to the binary choice model, but now things are a little bit more complicated actually. The parallel is that we can also calculate marginal effects. However, in the binary choice model, we had one marginal effect, and that marginal effect was very meaningful. So the marginal effect we looked at was the change in the probability that y is equal to 1. So this was the bigger one of the two outcomes in terms of the coding. When I change xi by a little bit. And that was the derivative of the CDF of epsilon evaluated at xi beta with respect to xi. And that gave me the density of epsilon evaluated at xi beta times beta. Okay, a density is always positive. So what that means is that in the binary choice model, the sign of the marginal effect is always equal to the sign of the coefficient that I'm looking at. Now, in the ordered choice model, what I actually do have is capital J outcomes that can potentially be recorded. So yi can go from 1 up to capital J. For that reason, I get more than one marginal effect. And it's worth looking at this in more detail. So when you start from the choice probabilities that we looked at on the previous slide, then all you have to do is to take the derivative of those choice probabilities with respect to xi, and you end up with these quantities here. So for all alternatives j in between 2 and capital J minus 1, you get a difference in two densities evaluated at the two thresholds respectively times beta k, and beta k is the coefficient on the variable x that you're changing. What you see here is that for the first outcome, you get an expression that looks a little bit like for the binary choice model, and for the last outcome, you do get an expression that looks pretty much like what we had for the binary choice model. So here we have density evaluated at, well, now quantity that's a bit different, but then again a density times beta k. So what we had before, namely that the sign of the marginal effect is equal to the sign of the coefficient, still holds in this model, but only for the higher of the two outcomes. And that's exactly the parallel to the binary choice model. In the binary choice model, you have the outcome that is coded as a 0, and for that outcome, one would actually get minus the marginal effect for the 1. So that makes perfect sense because when the probability that y is equal to 1 increases, then the probability that y is equal to 0 must decrease because the two probabilities will add up to 1. Here in the ordered choice model, and that's important for you to keep in mind, is that the sign of the marginal effect for a given j is in general not equal to the sign of beta k. And the reason for this is this stuff in the middle, where I have beta k times the difference in two densities, the difference in the density evaluated at one value minus the difference minus the density evaluated at another value. Okay, and that difference can be positive or negative. And that follows directly from the math here. I'm going to show you a picture in a few seconds that will explain what's going on an intuitive level. Good, but before we get there, observe that for j is equal to 1, the marginal effect and beta k are always of the opposite sign, whereas for j is equal to capital J, they're always of the same sign. And that last thing is the parallel to what we have seen for the binary choice model. Again, also here the reason is that choice probabilities sum to 1, and because of all that, and because it's so complicated, what people usually do in the when they use the order choice model is they do not focus on marginal effects, but they focus on coefficients, and they focus on making sense of coefficients because these oftentimes nicely summarize what one is interested in. But this is really application specific. Here is the picture I talked about. So what we have here is the exact same picture as we had before once we look at the dashed lines. Okay, so these are the thresholds that we had before, the dashed vertical lines. Now let's think of beta as being positive. What will then happen once I increase xi a little bit is that these three thresholds will all move to the left because I'm subtracting more from alpha 1, alpha 2, and alpha 3. Okay, so I'm going from the dashed lines to the solid lines here, here, and here. Okay, so what is now the marginal effect? Well, the marginal effect for the first alternative is clearly signed, so it has to be negative. The marginal effect for the second alternative is, well, it depends, right? So here what we see in this example is that this is gained, this area, and this area here is lost. Okay, so you gain less than you lose, so that means that the marginal effect has to be negative. For the third alternative, it's the opposite. This is what is gained. We go from the dashed line to the solid line, and what we lose is this area here, because we go from the dashed line to the solid line. So a positive marginal effect. And here for the last alternative, yi is equal to 4, what we do get is that the marginal effect is positive. So here the marginal effect is of the same sign as the coefficient, as my beta. So what you see here is that what matters is the difference in the density evaluated at a higher threshold and the density evaluated at the lower threshold. And let me just go back one slide. So here you see exactly how it works. It's the density at the higher threshold minus the density at the lower threshold, and then with a minus. Okay, so let me go here again. Higher threshold, lower threshold. That difference would be negative, but then times -1, so it's positive, and this is exactly what we got before, that the marginal effect on the probability that yi is equal to 3 is actually positive. So this is how these marginal effects work out in the ordered choice model. Good. So what I'm going to do now, now that we've actually already covered the entire model, if you like, is I'm going to talk about two structural models that are quite famous in the literature, where in the end of the day, we're estimating a version of an ordered choice model. And what this shows you is that there can be quite some economics going on in the background, and these two structural models kind of nicely illustrate that. So the first one is really a model of industry structure, and this is a paper by Bresnahan and Reiss from 91. And in this paper, what they look at is entry choices. Okay, so they ask the question, in the market, what can explain how many firms are actually active in that market? What is the underlying interest? The underlying interest is to learn about the dependence of the nature of competition on the number of firms in a market. When you have one firm in the market, you would have a monopoly. So when there's a monopoly, then the suspicion is that the monopoly would charge prices that are too high, because that's profit optimal for the monopolist. And the more firms there are in the market, the more prices will actually decrease. But of course, what you observe in data is that in some markets you have many firms, and in some markets you have less firms, and that is of course endogenous. And this is exactly what they model here. So what they do is they specify industry profits in the following way. They say industry profits when there are n firms in the market are the market size, and these would be the number of people who are around, population. Then we have variable profits per capita, so per inhabitant of, say, a city, minus fixed cost. And then on top of that, you would have an econometric error term. So that econometric error term captures all kinds of differences across markets. So the underlying idea here is that we have data with one observation per market, and we do something that's a cross-sectional analysis across markets. And the key variation that we're going to exploit is variation in S. Okay, so we're going to look at small cities, big cities, and we're going to look at the number of firms in small and big cities. And we're going to think of an underlying trade-off between variable profits and fixed cost. So when you have more people in a market, when more people live there, then there can be more firms in that market, because more firms mean more fixed costs, but more people in that market also mean more variable profits. Okay, so there are more variable profits to cover fixed cost. And the underlying idea is that when you have too few firms in such a market, then there will be entry, right? There's, say, money on the table. It costs a particular amount of fixed cost to be active in that market. And if one is active in that market, then one can earn some variable profits. So what will happen is that there is entry until industry profits are close to zero. and this is how they also think of this in this paper. So to be specific, Y here are measures of market size. So think of this as measuring how many people live there. And Z and W will shift per capita demand and costs. As I said, epsilon is a standard normally distributed error term that gives us profit shocks. So in some markets, the epsilon will be higher than in other markets. And that will explain that in those markets, even if Y and Z and W are exactly the same, in some markets we will observe more firms than in other markets. We'll get to how this works in a minute. Before we get there, what's useful is to define entry thresholds, Sn, as the market size so that n firms earn 0 profits when epsilon is equal to 0. So what you can do is you can start from this equation here. You set epsilon is equal to 0. And then what you do is you solve for S. Okay, so you see directly that S must then be equal to F divided by V. Okay, and that will be called the entry threshold. And so S2 would be the number of inhabitants I need when epsilon is equal to 0, so that 2 firms make exactly 0 profits. And then I have S3, S4, S5, and of course what I will have is that in order to have 3 firms, because of fixed cost, to make 0 profits, I will need more inhabitants in such a market. So S3 is going to be bigger than S2 and so on. And all this business here, net of the error term epsilon, will be denoted by pi bar n. And again, what is my data? My data is n, basically S, and these measures Z and W. I'm not going to observe profits, and I'm not going to observe epsilon. If I would observe profits or revenues, then I could do more, but I don't observe that here. Okay, taking this Sn as an object that is kind of interesting, what we can show is that entry has no effect on the nature of competition if the costs are the same for all firms. So if the Fn, if there's a certain symmetry in the Fn, in the sense that the last firm entering has the same Fn as the first firm entering, and each firm earns the exact same variable profits, then what we have is that the number of people I need per firm will not depend on the number of firms in the market. So I'm looking at a slightly bigger market and I'm looking at a slightly smaller market. In the bigger market, I have n+1 firms. In the smaller market, I have n firms. I do estimate that model, and we'll see in a minute how that works. And if I can then show that the number of firms, the number of people I need per firm when there are n firms in the market is equal to the number of people I need per firm when there are n+1 firms in the market, then I can conclude that entry has no effect on the nature of competition. And what we can think about here is that entry will not change the price level for consumers anymore. Good. So how do we take this model to the data? We take this model to the data, and that's why I actually kind of like this paper here, and why I like to present it here at this point. We do exactly the same thing as we did before. We just have to derive the implied choice probabilities, or the implied probabilities. Okay, so we're going to observe in our data the number of firms in the market. So what we need to do is we need to derive the probability to observe no firms in a market, the probability to observe n firms in a market, or the probability to observe 5 or more firms in the market. And these choice probabilities are, in the end of the day, very, very similar to ordered probit choice probabilities. So let's look at this in more detail. The probability that there are no firms in the market is equal to the probability that industry profits when there's one firm are negative. Okay, and when I write out industry profits, then this will be pi 1 bar plus epsilon is less than 0. What I get here is, just a sec. The probability that pi 1 bar plus epsilon is less than 0, or the probability that epsilon is less than minus pi 1 bar. So this should be a pi 1 bar. And we have seen already before that the probability that epsilon is less than minus pi 1 bar will be equal to 1 minus the probability that epsilon is less than pi 1 bar. And this is this quantity here. So with the one change that this should be a pi 1 bar. Good. So this is a very similar expression as we had before. The probability that n is equal to little n is then, by more or less the same token, the probability that industry profits when they're small n firms are positive or non-negative, and when they're n plus 1 firms, they're negative. Okay, so that would generate n firms in that market. And then again, as in the ordered probit model, you would get the difference between two CDFs of epsilon evaluated at, here in this particular case, pi n bar and pi n bar n plus 1. Okay, and notice, by the way, that pi n is going to be weakly decreasing in n in this model usually. So pi bar n is denoting industry profits net of epsilon. And when I'm only changing the number of firms in a market, what this will do is it will increase fixed cost, and it will usually decrease or not increase at least variable profits. So for that reason, pi n bar will be weakly decreasing in n. And then the last choice probability, or the last probability for this model, is the probability that n is at least 5. So that will be the probability that industry profits for 5 firms are non-negative, and that will be the probability that pi 5 bar 5 plus epsilon is positive, and that is the probability that epsilon is bigger than minus pi bar 5, and that can be written as the standard normal CDF evaluated at pi bar 5. Okay, now we have one thing here that is a little bit non-standard as compared to the ordered probit model, which is the dependence of one component of pi bar n on n actually. So if and this is variable profits, so if variable profits would actually not depend on n, then we would exactly get a standard ordered probit model, and then we wouldn't even have to code up this model here in say MATLAB, okay, to estimate it. So then we could use any statistical package that has the ordered probit model implemented. Here what we can do is we can just program this up using these choice probabilities and estimate the model. So what they did was to use the following specification. We have these three objects, market size, variable profits, and fixed cost, and they specified things in the following way. So they said market size is town population with a coefficient of 1 in front, plus other measures of population with coefficients in front. Okay, so here what they allow for is that nearby living people do come to town to visit one of those firms. Variable profits have some shifters X. These shifters consist of variables Z and W. We'll see what these are once we look at the coefficient estimates. But importantly, we have lots of alphas floating around here. Okay, so the first, a market with one firm active would have variable profits alpha 1. A market with 2 firms active would have per capita variable profits alpha 1 minus alpha 2. 3, it would be alpha 1 minus alpha 2 minus alpha 3, and so on and so forth. And for fixed cost, what we have is we have shifters of fixed cost. So these WLs are going to be observed variables, and they're going to have coefficients, gamma L, and they're going to shift fixed costs across markets. And what we have here is a specification where fixed costs with 1 firm active would be gamma 1, with 2 firms active would be gamma 1 plus gamma 2, 3 firms active would be gamma 1 plus gamma 2 plus gamma 3, and so on and so forth. What this allows for is that later entrants have higher or lower fixed costs than earlier entrants. Once I use this specification, I can estimate the model, and I get coefficient estimates, say gamma hats and alpha hats and beta hats and lambda hats. And once I have those, I can calculate these entry thresholds, Sn. So that would be, again, the number of people I need in order to have 3 firms or n firms make 0 profits. Okay, and this brings us back to our discussion of marginal effects at sample average x's, or average marginal effects, in the sense that one has to think about the values w and x at which one does actually evaluate this expression, and what they do is they evaluate it at sample average WL and sample average X. And that's just one way of doing it. It will probably not matter much in practice. Good, so let's look at the data a little bit. So what you see here is dentists by town population. This is the sort of stuff they look at in the paper. What this figure shows is that when town population in thousands is between 0 and 0.5, so when between 0 and 500 people live in some town in the US, and what they look at here are isolated towns, so that they can abstract from interaction across towns and people traveling between towns. When population is between 0 and 500, then what you see is that in most towns there is no dentist, and in some towns, about 20%, we do have 1 dentist. Okay, so when population is between 500 and 1,000, then we see these are the ones with no dentist, these are the ones with 1 practice, and these are the ones with 2. Between 1,000 and 2,000, 0, 1, 2, and then in the figure below you have also 3. Okay, but none with 4 or 5 plus. And then, when you look more to the right, you see that towns with 7 to 8,000 people, what we observe are either 3 or 4 practices in those towns. So this is descriptive evidence. Here are the estimates. This table, no, these are not the estimates, these are descriptive statistics to give you an idea about the variables they do have. So the dependent variable is the number of firms, and what they look at here are doctors, dentists, druggists, plumbers, and tire dealers. For population, what they use is town population, so that would be the variable with a coefficient of 1, and then you have additional population measures, for instance, nearby population. And then here, these would be the variables in X. No need to go into detail here. Here are the estimates. So what you see here is a table with 5 columns. So they've estimated per type of firm. And by the way, they got the data from phone books. Okay, so this is a paper from 91. It's not that admin data were widely available at this point. So, but what you could of course do is you could just take phone books and look up how many tire dealers there were in a particular town, and then you take census data and you put into your data set all these other measures, and then you can estimate the model. Quite a smart way of doing it, I would say. Population variables here first, then we have these betas, and the most interesting variables are these alphas and gammas down here. So you get lots and lots of coefficients. Rather than looking at those, let me look at these fitted entry thresholds. So what you find here is estimates like this. Okay, so for doctors, what you need when epsilon is equal to 0 is 880 people to live in a town, so that you get entry of 1 dentist. Okay, and then the second one comes in when you have 3,490 people. The third one comes in when you have 5,780, and so on and so forth. Okay, so what you see already here from these numbers is that you need about 3,500 to have 2, to have the second one, and you need not even 8,000 to have 4. Right, so a certain proportionality is coming into play, starting at 2 already, somewhere between 2 and 3. Okay, and you see this also a little bit already, for instance here for druggists. So for 3 I have like 5.04, and here I have 7.67, and here I have 9.39. Okay, so there is a certain proportionality going on already here. Same for plumbers and tire dealers. But this becomes clearer once one looks at these entry threshold ratios. So let's take the number of people per firm when there are 2 firms relative to the number of people per firm when there's 1 firm. Then we get these numbers here, 1.98, and then 1.1, 1.95. And I said before that when this ratio is actually equal to 1, then this means that the nature of competition doesn't change much anymore. And I was probably a little bit fast actually when I said this. I didn't really say this before, so I didn't really discuss this before, but it was on the slide here. So this is the entry threshold per firm, or the entry threshold, the entry threshold per firm for n firms in the market. And here I have the entry threshold for n plus 1 firms in the market. So I can, of course, calculate this quantity here. I can calculate this quantity here, and I can take the ratio of these two. And if the ratio is close to 1, then it would be the case that entry has no effect on the nature of competition. If, and that's a big if, of course, if costs are the same for all firms, so if there's a certain symmetry going on in the background. Good. So what they do is they also do tests. They do likelihood ratio tests for equality of these per firm entry thresholds. So this tests basically whether we have equality to 1. So and they look at various combinations, so that little s4 is equal to little s5. So the little s is always capital S divided by capital Sn divided by n. Capital S5 divided by 5, capital S4 divided by 4. So this tests whether this number here is equal to 1. And what you see is always a star when the hypothesis is rejected. So you see a rejection tentatively when 2 is included, as 2 is included. Okay, so one way to interpret this, abstracting from dentists, where we see this rejection also here when 3 is included, is that 3 firms is enough. Okay, so in the sense that starting from 3, the nature of competition doesn't, starting from 3 firm or entry of the 3rd firm, the nature of competition doesn't change anymore when I have more entry. In the sense that when more firms enter, then it will not be the case that consumers get a better deal in the sense of consumer surplus. One way of illustrating this is figure 4 in the paper, which is kind of nice. So as I said, when the ratio between these two little s's is close to 1, then the nature of competition doesn't change much anymore. So what you see here is that there is quite a change here, of course, and here, but starting from 3, for all industries, that ratio is close to 1. Good. So this brings me to the other paper I wanted to talk about. And that paper is by Smith, Kapteyn, and Van Soest from 2007. And this is less of a structural paper in the sense that there's a big economic paper, economic model in the background, but it is a structural paper in the sense that they're trying to disentangle 2 things that are going on at the same time and that are generating our data. So what exactly do I mean by that? So what I mean by that is that differences in answers to a survey question can arise for at least 2 reasons. So it could either be that there are fundamental differences of some sort, or because there are simply differences in reporting behavior. And what they use in this paper here are so-called vignette evaluations to recover differences in reporting behavior. And once you recover those, once you measure those, you're able to estimate differences in the underlying, more fundamental relationship, and that might be of interest. What they do is they do this in the context of self-reports on work disability, focusing on the question, what is the difference between the US and the Netherlands? So a nice figure that they have in the paper is figure 1. So here they talk in this example simply about health reports, self-reported health. Okay, so you can report your health to be poor, fair, good, very good, or excellent. There's an underlying distribution of latent health that is then translated into reports. Okay, and what you see here is a picture with two underlying distributions. So in country B, the distribution of health is to the right of the distribution of country A. But what you also see is that these reporting thresholds are different between the two countries. Okay, and in particular, what you see is that in country B, they're to the right of country A. What do you see in the data? In the data, you see only the reports. So these are the areas basically underneath the curves. Not basically, these are the areas underneath the curves that correspond to the probabilities that a certain report is made, which is then the fraction of reports in the data. So this would be the fraction of people saying that they're in excellent health. So in country B, that is smaller, as you can see, than the fraction of people reporting that they're in excellent health in country A. Yet, as you can also see, and as I said, the distribution of underlying health is actually to the right in country B. So in the data, it looks like people in country A are more healthy, but in fact, it's the case that people in country B are more healthy. It's just that they have a different way of reporting about their health, and for that reason, one might draw the wrong conclusions if one were to look at only those reports. To substantiate this, what the authors do is they show by age group how many people are disabled, in the sense that they can't go work. The disability rates for the United States are lower than for the Netherlands. And at the same time, what you do see is that the health conditions suggest that people in the United States are of worse health than people in the Netherlands. So what do they do? In order to learn about differences in reporting behavior, they do something that is more common in other social sciences, and that is called vignette evaluations. So what they do is they describe hypothetical individuals, and then they ask respondents not only to rate their own health, but also to rate the health for these hypothetical individuals. Here there's something in table 2, so we get summary statistics on these reports. What we see here is reports for the Netherlands, reports for the US, and here these would be the so-called pain vignettes. Somebody is described who has some form of pain, and then the question is asked, is this person limited in his or her ability to work? And then people can say not at all, mildly, moderately, severely, extremely. And then what you see here is that in the US, the not at all answer is more common than in the Netherlands, even though the exact same person has been described. Then people are also asked about themselves. Are you limited in your ability to work on the exact same, using the exact same alternatives that people can choose, and everything is then brought together using a generalized version of the ordered probit model that we have seen before. I can't go too much into the details. I can just give you a glimpse into what's going on. So for that reason, let me go back here. What you see is that you have a response equation that looks like this. So there's a latent variable that looks pretty much like the latent variable we did have. We have an error term, and we have in equation 2, we have these thresholds basically. So they're called tau here in the model, but in the end of the day, this is pretty much the same thing. The specification here has actually the thresholds depend on another index. So the thresholds would be the threshold for the first alternative. No, I'm sorry. The threshold for the first alternative is specified like this. And then the threshold for all subsequent alternatives is going to be the previous threshold plus the exponential function applied to an index that is always like different from one threshold to another. So therefore, going from j-1 to j, you would have a parameter gamma j, and that is then the parameter on xi. So the difference between 2 would also depend on x. So it's a very, very general model. But in the end of the day, it is an ordered probit model. Notice, by the way, that the scale normalization in their model is different. I'm not going to talk about the details, but they have here a free parameter sigma square r, and then they talk about normalizations later. That's one part of the model, and the second part is the part where people evaluate those vignettes. And the way this is modeled is that the exact same thresholds are used. So we have again these taus, but of course the underlying health of a vignette, or the underlying ability to go work, should not depend on the individual characteristics. So that's modeled as a vignette fixed effect. So for each vignette question, there's one parameter estimated. And then on top of that, they do allow for the effects of the gender of the vignette person, but that's not important for us here. So they estimate this model, and I do realize that this is now too fast for you to fully understand what's going on, but I hope you get a little bit the idea. So again, you have an ordered probit model, standard ordered probit model, and on top of that, you use extra data on these reports on the vignette questions. And when you bring this together, what you can do is you can learn about, from the vignette answers, you can learn about the dependence of thresholds on individual characteristics, and in particular, you can learn about the dependence of the thresholds on the country in which people are living. So that's one, and once you have done that, you can learn about the dependence of underlying work disability on individual characteristics, and that goes back to the original questions about individuals' ability to work, and this then is all actually estimated simultaneously with random effects to make it a very flexible model. Good. The results are shown in table 3. So what you see here is in the beginning, this is a standard, this is a generalization of an ordered probit model without reporting effects. Okay, so this is what you would normally get. And so what you find here is, say the effect of female is minus 0.28. And this is not significant, so standard error is 0.26. But that means, like in the US, females are slightly less likely to be disabled. In the Netherlands, so there's an interaction between female and a dummy for the Netherlands. In the Netherlands, the report on work disability is so they're slightly more likely to report to be disabled to go to work, but again, it's not significantly different from zero, right? So what this shows us is how reports differ between the Netherlands and the US, right? So this is the interaction with the dummy for the Netherlands tells us how much more or less likely people say that they're disabled when they're, for instance, female in the Netherlands vis-a-vis the US. The complete model has two parts. So we have the parameter for the thresholds. So the variables here will have an impact on the thresholds, and they will have an impact on the relationship that is of interest to us. Let's just focus on the constant term. So here you see, by the way, the location normalization. So the constant term is lower here in the Netherlands for the reporting threshold. So that means the Netherlands has a lower value for all the thresholds. And that means that Dutch people, everything equal, are more likely to say that they're disabled to work. So on top of that, what we have is also a fundamental difference. So it seems as if the underlying relationship also changes. So that means that they're not only saying for the same level of underlying disability that they're more disabled to work, but they are also more disabled to work, holding everything else constant. So this, of course, has all the diseases in there, right? So this has all the health problems in it. And of course, what is actually happening is that Dutch people are less likely to have these diseases. So what that means in turn is that if you just compare between the two countries, then it can still be the case that Dutch people report to be more likely to be disabled, but at the same time are actually less likely. Okay, so this is because these diseases here are in the model. And the final thing to notice is that this effect here, so this is the difference between the two countries, and this difference is, as I said before, coming from two sources. One is the difference in the reporting behavior, the other one is the difference in the true underlying health, let's say. What's interesting is that this number here roughly is equal to this number here minus this number here. Okay, and this is not completely surprising because in the ordered choice model that we had before, we actually did always have this thing that it's a difference in the alpha and the x beta, right? That matters. If the alpha also depends on x, which is something we can't normally find out using the normal data without vignette evaluations, then one would expect actually that it's this minus that. So this will then become about minus 4.99. So this is not exactly the same, but when you look at other coefficients, say minus 26 is minus 102 plus 51, so that will be 50. So it goes in the right direction. Okay, so it's not exactly the same, but you can, once you know these two, you can kind of guess what you will get here. Good. What you could now see here is that you can start from the standard ordered probit model, and you can generalize it quite a bit. Okay, so the generalization here would be that the reporting thresholds depend on characteristics, and one characteristic would be the country people live in. But what you do need in order to estimate such a model is extra data. Once you design a survey, you can make sure that you collect these extra data, but you need to do that. So that's what you can take away from this second paper that I showed you. From the first paper, the paper by Bresnahan and Reiss, you can take away that you can have a very rich, very econ-y model that explains what is going on in your data, and you can use that model and bring it to the data using an ordered probit structure again. And once you've estimated the model, you can interpret what you get in terms of parameters in a very structural way, in the sense that you can really talk about economics when you calculate these entry threshold ratios. So you can make then statements like 3 firms is enough, and you can do that because you get a lot of mileage out of the model structure, and you don't need terribly much data to then actually at least get some idea about what might be going on and what might give rise to low prices. So whether you need 6 firms or whether 3 is enough, questions like this you can answer by combining relatively little data with a model structure that fits well to what's going on. Good, so this ends my discussion of order choice models. I hope you got the impression how this all works, and I hope you also see that there are quite some parallels to what we have discussed before in terms of normalizations, marginal effects, the general model structure, and that you can get the binary choice model as a special case of the order choice model. Thanks for watching and all the best.